Hello Math 1324 students. Let's begin lesson 9, quadratic functions. A quadratic function is a function of this form. Y equals to ax squared plus bx plus c, where the leading coefficient a is non-zero. If a is 0, then this part just drops out because that's 0, and we end up with bx plus c. So that's going to be either linear or less, no longer quadratic. And that's why this condition a non-zero is important. Furthermore, this quantity a is particularly important in a sense that it determines the general shape of the graph. Let me show you a couple of examples here. When a is positive, the leading coefficient is positive. In general, we get this kind of graph, a parabola which is concave up. When a is negative, on the other hand, we get this kind of graph in general, a parabola that is concave down. Minimum here, concave up, and maximum there, concave down. Now, why is that? Why does the shape, the general shape, completely dependent upon the sign of a? Well, that's going to be answered in the next subsection here, the end behavior. Now, this may be a bit too advanced for some students here. End behavior is important in STEM algebra, but it's not really emphasized here. But for quadratic function, let's do a certain amount of end behavior. Basically, we do these kind of asymptotic estimation. When x is very large in terms of absolute value, in other words, x is either very positive or very negative. So in number line, very positive is to the right, and then very negative is to the left. So it's either right hand or left hand. That's why we call this end behavior. Now, when x is humongous, either positive or negative, then the leading term, ax squared, contributes a lot and the others do not. Very little. For instance, when x is, say, for example, 1, then x and x squared, they're the same. But x is less than 1, for example, then x is, say, 0.1, then x squared is 0.01. It's smaller. And when x is 0.01, then x squared is 0.00001. 0.1 squared. 0.01 squared, so 0.0001. Anyway, it's smaller. So x squared contributes less. Now, on the other hand, when x is bigger, like 10, then x squared is 100. So x squared contributes more. Now, x is 1,000, then x squared is million. X is a million, then x squared is trillion, and so on. So the bigger the x value is, the more important this quadratic term, comparatively speaking, the others. So when x is humongous, the other terms do not contribute very much. Just meager compared with the humongous contribution from ax squared. So you can pretty much assume the behavior is more or less the same as that of ax squared. Now here, look carefully. Ax squared consists of a times x squared, and x squared is always positive. You see, x squared is always positive, and x is going to either plus or minus infinity, so x squared is always going to positive infinity. So whether this entire thing is going to infinity times a, which is either positive infinity or negative infinity, depends completely upon the sign of a. When a is positive, this entire thing is positive infinity, so y coordinate is going up. When a is negative, this entire thing is negative infinity, so y coordinate is going down. Keep that in your mind and look at the graph. The same graph again. I am moving to the right or to the left. Either way, y coordinate is going up. Up. Because we have ax squared behavior, x squared is always positive, you see. The others do not contribute very much, so you can ignore those when x is large. To the right or to the left, either way, y is going up because a is positive. Positive infinity is going up. Now look at the second graph here, red graph. Precisely the opposite. This time a is negative, so we go to negative infinity, either to the left or to the right. So x is going to right hand plus infinity or left hand negative infinity. Doesn't matter because x squared is still positive always, and a times positive, so overall negative infinity. Going down here, down there. So the end behavior depends completely upon the sign of a, and that's why we are having this concave up when a is positive and concave down behavior. Here's a grand summary. When a is positive, we have parabola concave up, and we have minimum k right here, as you can see, and let's say k is minimum, then the range is k to infinity. Start from k, and then I can go up forever. Domain is always negative infinity, positive infinity. I mean, quadratic expression is always valid, so to the left, to the right, no problem. Whether it's going up or down, that's a problem here. And for concave up, you can go up, but not down. Nothing below the minimum. Now let's look at the right-hand side graph. Concave down when a is negative, and we have maximum k right here, and consequently the range is negative infinity to k. You can go down forever, but you cannot go past k up. So that's the maximum, because either way, to the left or to the right, we have to come down. Alright, so much for the summary. Now let's have some applications based upon the general form. The simplest application is the intercept problem. Y-intercept is easy. Put x equals to 0 and find y. And what do you get? X is 0, so that's 0. X is 0, so that's 0. All you have is c. Too simple, right? Okay, that was too simple, but the other one, that's a bit worthy. Put y equals to 0 and find x. So y is 0, y equals f of x is 0. So this entire expression is equal to 0. What do we have? We have a quadratic equation. So you can factor it, you can do whatever. In general, we have quadratic formula like this. And the square root may be valid or maybe not. Depending upon that, we may get two real solutions or just one double root or no real solution. Let's have some examples. Find the y-intercept. Well, y-intercept, that's too easy. Plug in x equals to 0, then we get negative 15. Y equals to 9. And finally, y equals to 2. So y-intercept, I wouldn't bother. X-intercept. We have to set this entire thing equal to 0 because y is equal to 0. And there you go. Oops, wrong cell. Set this entire thing equal to 0. It turns out you can factor it. The detail is left to the student. If you factor it, 2x minus 5 is 0 or 2x plus 3 is 0. So we get either one or the other. And here is a graphical justification. 5 halves right here or negative 3 halves right here. Make sense? So set up the quadratic equation, factorization, and they correspond to the graph, the x-intercept. Here's another problem. Set this equal to 0. Okay, I wouldn't bother y-intercept, that's too simple. X-intercept, set it equal to 0. It turns out you cannot factor this, so you have to rely upon the quadratic formula. It turns out square root of 112 can be simplified. Square root of this 112 can be divided by 16, so we end up with this kind of simplification. But that's perfectly fine with me. Anyway, we have these solutions, and we have a graph like this. Here and there, we have the x-intercepts. And finally, the overall shape is concave down because a value is negative. So the graph versus the x-intercepts. Time for one more? Okay, all right, just one more. Let's do this. Again, x-intercept only because y-intercept is just too trivial. You see, that's too trivial. X-intercept. Set it equal to 0 and it turns out we have a complex solution. Square root of 9 minus 16, so we get a negative number inside the square root. So that means there's no real root. In other words, there should be no x-intercept. Let's see. Is that really the case? And indeed, yes. A value is positive, so concave up. But the minimum value k turns out to be positive as well, so there's no crossing. So no x-intercept. Okay, so much for the applications, both theory and applications associated to the general form of a quadratic function. We're going to talk about other forms such as vertex form and intercept form in separate videos. Especially the vertex form is important. Stay tuned.